Hello to all of you. Today's discussion topic is logistic regression in R. Basically, we are using logistic regression when our response variable is in category. By category, I mean it is in dichotomous. Its nature is dichotomous. For example, male, female, urban, rural, literate, illiterate, biased, non-biased. So in such scenario, we are using logistic regression. What can be the examples of this? The examples are: a customer will buy the product or not. A doctor wants to accurately diagnose that this tumor is malign or benign. A loan officer wants to know whether the next customer will default or not default. So in such scenario, we are using the binary logistic regression. The word itself says that it's binary, 1 and 0. Why we are not using discriminant analysis? Because in case of discriminant analysis, we require multivariate normality. The assumption of multivariate normality should be met. If it is not met, then we cannot use discriminant analysis. But in case of logistic regression, these assumptions are smoothened or rather relaxed. Therefore, we can use it. We can also consider logistic regression as the non-parametric version of discriminant analysis. Let us understand one example that we are having a data in which we are having something that the gender is on one side and they will purchase a branded product or not. So male purchasing the branded product, female purchasing the branded product, male not purchasing the branded product, female not purchasing the branded product. So male purchasing the branded product, 34 are there, 25, female purchasing the branded product, 23, female not purchasing the branded product, 27 people are there. Okay, now we will take the ratio of it. So 34 divided by 57, 23 divided by 57, I'll get the number 0.596, 0.403. 25 divided by 52, 27 divided by 52, I'll get this figure. I'll also consider the overall ratio, that is 57 divided by 109, it is 0.522, and 52 divided by 109, 0.477. Now we will have to understand the concept of odds ratio for interpreting the logistic regression. What's the odds ratio? Purchase to not purchase. So here 0.522 divided by 0.477, it turns out to be 1.094 divided by 1. It means that the probability of happening the event of purchasing the branded product in comparison to non-branded product is 1.094. If I talk about conditional odds, in case of males, what is the scenario? Let's see, 0.596 divided by 0.480. If I take the ratio, it is 1.241. So in case of male, the probability, that is the success of purchasing, see here we will have to define the success because we are coding everything in case of 1 and 0 because the response variables will be in 1 and 0. So if I say that purchasing a branded product is a success, then probability of happening this event is 1.241 times more than not purchasing the branded product. Purchasing the branded product and not purchasing the branded product. In case of female, it is 0.403 divided by 0.5, it is 0.806. So if we consider purchase as a success, then the probability of happening this event is less in female. What's the overall odds ratio? It is 1.241 divided by 0.806. I get the number as 1.539. So males are 1.539 more likely to purchase branded products in comparison to females. So if I say that the probability of the success is 0.80 and the probability of the failure naturally will be 0.20, this means that the odds of success are 4, or the success is 4 times more likely to happen than failure. Conversely, we can also write that the failure is more likely to happen 1/4 rate of the success. If I take the odds ratio, if I explain this thing by the Smellies, odds is equal to success divided by failure. What is the probability of the success? It is success divided by total success plus failure. And failure is failure divided by the total of success plus failure. So what is the difference between linear and logistic regression? In linear regression, the response variable, the dependent variable, can take any value between -infinity to +infinity. But in case of logistic regression, we are range bound. The value of the dependent variable should not go beyond 1 or should not go below 0, and that's a basic difference in case of linear and logistic regression. Logistic regression derives its name from the concept of log transformation, which we are carrying out on the equation. What are the approaches of logistic regression? See, basically we are coding here everything as 1 and 0, and therefore 1 represents a success and 0 represents failure. Be very careful in assigning the codes, because your entire interpretation of the logistic regression will be based on what you are coding, anything as 1 and what you are coding anything as 0. Now let us understand this concept on a graphical approach. See, in case of linear regression, if I say x-axis and y-axis, your linear regression is continuous in nature, your line is continuous. But in case of logistic regression, there is a break. Beyond some point of x, the value of y will remain constant, and after that there is a break, and again it will become constant. If I reorient the axis, I will get something like this. There are purchasers and non-purchasers of the product. So now, which is a curve, or which is the mathematical function which best suits this, is a logit curve. Exactly, it will fit this type of case. Now, this is an example of poorly fitted logistic curve. Now, why it will happen that your curve cannot fit properly? See, whenever we take a response variable, we have to be very careful that whatever we are taking a response variable in such a way that the categories are crystal apart, or rather say are crystal clear, or they are poles apart. That's like north and south pole. Bias, non-bias, very clear. Purchasers, non-purchasers, very clear. But when I talk about moderate users and light users, there is a confusion. When we will have such overlapping cases where the response can be on either side, in such scenario, your logistic curve will not be able to fit properly. Now, this is an example of well-fitted logistic curve in which there is no overlap. See, here there is an overlapping C. You can see this logistic curve is not able to properly predict that this is in 1 or 0. See, but when I talk about this, it's you can say the classification has been done appropriately. Regression analysis is more used for prediction, and logistic regression is more used for the it's a classification technique. Discriminant analysis is also a classification technique. Now, what changes we are doing in the basic regression analysis so that we can carry out the logistic is, let's understand the functional form. Y is equal to this equation which we have studied in linear regression. When I make it as a function of the probability, that py, probability of the occurrence of event, it's equal to 1 upon 1 plus e raised to minus this equation. So when I will do some, you can say simplifying the equation, I'll get 1 upon 1 plus e raised to the equation. So now if I again simplify it, I will get e raised to the equation upon 1 plus e raised to this equation, and if I rename it, it is e logit upon 1 plus e logit. So e logit is odds upon 1 plus odds. So when I make this as the function of odds, what I'll get, odds is equal to p upon 1 minus p, the probability of the success divided by probability of the failure. It's the same thing which we got in our previous slides. Now let's take one example. Let us go directly on one example. And the data file is empty cars, right? And the data file is empty cars. First of all, let me remove all this. Now in this, there are 32 cars are there of different brand. Let us see the variables also. Run. On right hand side, you can see that automatic is coded as 0 and manual is coded as 1. Remember one thing again, I am repeating again and again, whatever you code 1, the category as 1, the interpretation will be based on that only. So be very careful in this. So I want to say that I am creating a base model in which I am not assigning any independent variable to the model, any independent variable to the dependent variable. I am just running the model at present on the basis of the constant. So the model is AM is equal to constant plus error. The null hypothesis is that the coefficient of the constant is equal to 0, or rather it is insignificant. So when I'll run the model, I'm giving the name as base GLM, generalized linear model AM tilde 1, data is equal to empty cars, and I'll be using the family of the binomial. When I'll run this, and I'll get the summary of the base. First thing which you should observe is that the null deviance and the residual deviance is same. This should not be the scenario. Residual deviance should be very less than comparison to the null deviance. It is exactly like this is explained variance and unexplained variance, right? Now I got this value as minus 0.3795. right? This we will understand later on. We'll keep this thing reserved right now and again go back on the PPT. Now if I manually do some calculations, that there are total 32 cars, manual is 13 and automatic is 19. The probability that the car is automatic is 19 divided by 32. So I get this number as 0.593. Probability that the car is manual is 1 minus 0.493. It is 0.406. Right, see, it's 0.406, 1 minus. Probability of success, probability of failure. The odds ratio that the car is automatic as opposed to the manual car is 19 divided by 30. Likewise, the odds of manual car as opposed to the automatic car is the inverse, 13 divided by 19. It's 0.684 is to 1. Now, the number which we have got, 0.379, this number, what is its interpretation? Let us see. So I got the model. The base model is that AM is equal to AM. I am writing manual is equal to 1 because the interpretation will be according what I have coded as 1. So AM is equal to minus 0.379 plus error. So the intercept minus 0.37, which corresponds to the log odds for the car being manual because it's a reference category. Automatic is 0. The logic can be converted back to an odds ratio. So I want to convert this log of odds into again odds ratio and I want to compute the probabilities. How can I do it? Whatever the coefficient is there, I will take the exponent of it. So exponent is equal into bracket minus 0.379. You can do this on your scientific calculator or just write down in Google also. In Google also it will work. Write down exponential minus 0.379. It will give you the value 0.684 is to 1. Now substitute this value in our original formula. Odds is equal to P upon 1 minus P and 0.684 is equal to P upon 1 minus P. If I recalculate the probability by solving this, I get P is equal to 0.406. The probability that the car is automatic is 0.406. Now this number is exactly the same number which we got according to the manual calculation, right? This is the base model where we have not assigned any independent variable to the dependent variable. Now we will go for assigning the variables to the dependent variable, and I am creating another model that is fit 1. I am saying that the car maker, what are the factors or the variables which are influencing the car makers that our car should be automatic or more manual? Is it the mileage of the vehicle, the horsepower of the vehicle, the D-rate of the vehicle, the weight of the vehicle? That I want to see. So how can I see? Null hypothesis is that the coefficient of all these variables are equal to 0, or rather these variables are not at all contributing in taking the decision that the car should be manual or automatic, right? The desirable thing is that we should reject the null hypothesis. I am running the model fit 1 GLM models AM tilde MPG plus displacement plus horsepower plus weight. Family is binomial. Run. And I have got some estimates. This is for constant MPG 1.13 times of MPG, displacement is minus 0.0 into displacement, HP is 0.108 into HP, minus 4.805 into weight. So I have got this model, this one, the first model. Now I cannot interpret anything from this model because the problem is here. There is the p-value of any of the variable is not at all, you can say, significant. The p-value is not at all significant, or rather it is more than 0.05, and therefore we can say that these variables are not at all contributing towards deciding that the car should be automatic or manual. Right, let's proceed further. So now we will have to that we will see later on also. First let us run ANOVA. Now this ANOVA will tell us that which is the most significant variable which will contribute in deciding that our car should be automatic or manual. So here I get the variable as MPG and horsepower. Definitely you will have to also run the residual diagnostics by running par-mf-row C2/2. I will divide the screen into 2/2 and I will get the plot of residual. How to interpret about this residuals, that we have seen in our linear regression video. See my playlist in which there is a video of linear regression analysis in R. we have interpreted about this. Now I'm running another model, that is fit2, by surrendering, or rather not including displacement in our model. Why? Because displacement is having the highest p-value, and therefore we are surrendering it, and therefore we are making a new model. AM is equal to B0 plus B1 into MPG plus B2 into HP plus B3 into weight. Null hypothesis, or the coefficient of all these variables are insignificant or are equal to 0. I am dropping displacement from here and I am running it. Now what I get is the p-value of the weight has become significant, or rather the p-value is less than 0.05, and therefore I can say that the weight is significantly contributing in deciding the car should be automatic or manual. But how to interpret this? Let's go in the PPT and let's try to understand this part. This is the model which we have got. Fit2 is equal to minus 15.721 into 1.557 times of MPG plus minus 0.025 into displacement plus 0.108 into HP minus 6.954 into weight. Now what you will have to do, you will have to take the exponential of the coefficient. You can see here the exponential of the coefficient, and the value which you get is 0.00 minus 1 into 100. So I'm getting minus 100%. It means that the weight is definitely contributing, but it is contributing towards a car being automatic. Why? Because the one is coded as manual. Is it clear? One is coded as manual. Another thing which you should observe here is that the null deviance is 43 and residual deviance is 8. The residual deviance has also decreased, right? Residual deviance has also decreased. Okay, let's go back in the PPT and try to understand. Okay, the null deviance of the fit2 model is 43.22 with 31 degree of the freedom, and residual deviance is 8.761 with 28 degree of freedom. This is really a good thing that the residual deviance has decreased. Okay, but we cannot use this model because there are many variables which are insignificant here, and therefore they cannot be included in the model, right? And therefore we will have to remove this also. But before that, we will also have to run the confusion matrix. So let us run ANOVA plot, and again you see the residual diagnostics, are they proper or not. Now what's a confusion matrix? Let's try to understand. The confusion matrix is here, right here. Now just I'll give you a small example that in this pandemic we were using the COVID kits to identify, to detect that the patient is having COVID or not. So if I say COVID positive and COVID negative, a patient is having COVID positive or a person is COVID negative, and there are kits which are there. These kits are our model, and kit has detected that the person is positive or negative. Now what's a success for us? The success is that a patient is having COVID. A patient is having COVID, and the kit also detected that yes, he is having a COVID, and therefore that's a success. A person is not having the COVID, negative, and the kit also said that yes, the person is not having the COVID and that's negative. That's also the success because the kit is working properly. But there is a problem when the person is not having the COVID and still the kit is saying that yes, he is positive. Or there can be a scenario that the person is positive and the kit is saying negative. So these are all false positive and false negative. Now this also we can generate here. For this we'll be using the library caret. The command line is caret : confusion matrix as dot factor rounding of fit2 model, comma 0. 0 is a reference axis which we are using, reference category, automatic, as dot factor round AM 0, and this will give me the confusion matrix. No, I'll have to use here, I'll have to run the confusion. Okay. Now here you can see that it has given me same thing, the reference thing, it's actual data, automatic, and our model also predicted automatic. So 18 classifications have been done correctly. Original, manual is there, 1 is manual, and the model is also saying manual. 12 predictions are correct. correct classification, but there is one misclassification. Original data is saying it is manual, and the prediction, our model, is saying it is automatic. Similarly, original it is automatic and our prediction is saying it is manual. So there are two misclassified cases. Another thing which we have to see is the accuracy which we got. So 18 plus 12 divided by 32 is the 93 cases were accurately classified. When we'll be talking about machine learning, I'll talk in length about sensitivity, specificity, and predicted value, prevalence, and all that in the machine learning. But at present in this, you'll have to only focus on accuracy. Now I will have to surrender those models or surrender those variables which are insignificant, and therefore I'll go for model 3, where I'll not include now MPG, and I'm running the model that is fit3 run. Okay, now I've got the value of weight and HP. Now how to interpret HP and weight? Let's again go on the PPT. Now all these outputs which I am sharing with you, or rather this interpretation has been written in my book, which is available on Google. Just write down data analysis using Dhaval. Okay, all this I am sharing from my book only. All the codes are also there in my book. The interpretation is also there. The book is Data Analysis Using R, available on Amazon.in as well as Amazon.com. Okay, let's come back here. Now I have made the fit3 model. So I am having 0.0362 for HP minus 8.083 for weight. We have already discussed about the weight, that if it is negative, definitely it is going to contribute towards the car being automatic. Why? Because it is negative, and therefore the contribution will go towards automatic. It means that the more the car weight, the chances are there that it will be automatic. Now how to interpret about a horsepower? Again the same concept. I will take the exponential. Exponential of 0.0362 is 1.0368 minus 1. So it is 3.682 percentage. It means that with increase in horsepower, it is contributing towards the car being manual. How we can write technically? The odds ratio can be calculated by taking the exponential value of coefficient to get 1.0368, which means that we expect to see about 3.682 percentage. 1.0368 minus 1. Always take the exponential minus 1 in the percentage which you get is a contribution. If it is positive, it is contributing towards what is coded as 1. If it is negative, it is contributing towards what is coded as 0. Right? Let's try to understand this thing by the interpretation of coefficients. The MPG is there. If it is having a coefficient 0.04, the odds is 1.040. Right, that is based on the exponent E. If I take minus of this, if I convert it into a percentage, so MPG, as it is positive, MPG contributes 4% increase in the odds of car being manual because it is positive. Horsepower, take the exponential minus 1, 43.33 percentage contributing towards manual. Negative, weight is negative. So here minus 0.28, 28.8% decrease in the odds of car being manual. I am saying decrease in the odds of car being manual, or in other words, it is contributing towards car being automatic. Right? The interpretation of the manual car is done only as it is coded as 1. Okay, let's come back here. Shall I proceed further? Okay, yeah. I'll run ANOVA again. I'll see the plot. Now, if I want to see the coefficients of this, I'll write down the formula exponential fit3 dollar coefficients, and therefore it will give me the coefficients also directly. Again, the time is that we should run the confusion matrix. So library confusion matrix. Again, I get the same accuracy with the decrease in the variables. This is really nice. Even if we are decreasing the variables, I'm getting the same accuracy. Now there is a concept of parsimonious model, and that is with less number of variables, your model should be more accurate in comparison to over parameterized model. It means that we go on including variables in the model, definitely the things are going to improve, but that's the problem. It is a over parameterized model. Now once we have created the model, what's next? The next is, now we want to predict that if we are having any new case, then what? Okay, let me reorganize myself. So I am giving the information that there is a car whose weight is 2 and horsepower is 150. What are the chances that it will be automatic or manual? So let us consider this thing, you can say manually. First of all, let us try to calculate this thing manually, and then we will see on our system. Okay, so the probability that the car having weight 2 lbs and 150. Now we will directly insert these values in our original fit 3 model. Which model we have approved? Fit 3 model. This one. Yeah, this one. And we will try to find out what value I'm getting. So logit is equal to 8.124 when I will substitute the values here. Now if I take e raised to 8 power 8.124, I get the value 3374.49. Now when I convert this thing into the probability, that is e logit, e raised to 8.124 upon 1 plus e raised to 8.124, I am getting this as 0.999. It means that there is a clear-cut probability that this car will be manual, right? It's 100% chances are that the car will be manual. Now, if you recall this e logit, it is the same thing which we had discussed here. E logit upon 1 plus e logit, that is the probability of the occurrence of the event. Now let us check, am I getting the same result when I do it with the software or not? So I should get the value 0.999. Okay, let me go there and I'll run the model with the new data set, new data, run, and you can see my answer is same as we have done it manually. Now there can be a possibility that there can be a categorical variable in the model, right? And in our case, the categorical are vertical and the straight engine, which is coded as 1 and 0, as well as the number of cylinders. So first of all, I'll have to convert this into the factor. So I'm saying empty cars $vs as dot factor. I'm changing on the existing variable only. I'm changing it to the factor. So I'll run it. I'm also making the cylinder as factor, and I'm including Vs and cylinder in the model. When I'll run it, I'll get the answer. You can see Vs1. So whatever which is coded as 0 will become the reference category or will be captured by the constant, and what is coded as 1, its slope we will consider. Similarly, 4 is now the reference category there, which is captured by the constant. 6 and 8 are captured with the help of estimates. You can see that the Vs1, cylinder 6 and cylinder 8, their p-values are more than 0.05, and therefore they are not at all the deciding variables that the car should be manual or automatic. Now there are some measures which we will have to carry out. The first of all, that is evaluating the logistic regression model, that how far the model is good or what is the goodness of fit of this model. The null hypothesis is that the reduced model or the base model is true, right? And we will run it, and we will the null hypothesis is the reduced model or the base model is true, and the alternative is the current model is true. That is the explanatory power of the model is good. And I am running the test as lm test : lr test fit 3. I'll run it. So here the desirable thing is that your p-value should be less than 0.05 so that we can reject the null hypothesis, because in null hypothesis we don't have any model. It is in alternative hypothesis we are having the model, and the desirable is that we reject the null. And here the p-value is less than 0.05 because there are 3 stars in it, and therefore we definitely will say that it's a good model. We don't have the pure R-square in case of logistic regression because our functional form of the model has changed, and therefore we don't have the pure R-square. So instead of this, we are using pseudo R-square. In that also we are having various measures like Nagelkar R-square and Cox and Snell R-square. and I'll use the library Baylor at PSYCH because the pseudo r-squares are here. I'll load the library and then I'll run it. So you can see Cox and Snell r-square is 0.645. Nagelkar is also a good one. If I talk about McFadden, it is also a good one, and therefore adjusted McFadden is a little bit less, but most of them are nearer to 1, and therefore it's a good scenario. Now we also carry out the hosmerlemeshowtest, which can be done by using the package resource selection. So LEM resource selection : hoslem test fit3 $y fit8 fit3 g is equal to 10. What are all this? Let us understand. I write down help and hoslem test. Run. So if I talk about y, it is an expected value, and g is number of beans to calculate the quantiles. Okay. Number of beans to calculate the quantiles. So when I'm running this, I'll get the value as p-value 0.7627. Now here your p-value should be more than 0.05. I'm again repeating, your p-value should be more than 0.05 here, right? If the p-value is more than 0.05, it means that your actual data is fitting very well, or rather the model is fitting very well on the actual data, and this is what we want. We can also find out the variable which is of importance by using the command line caret : variable importance fit3, and it will give me the answer that a horsepower and the weight are the most, you can say, influencing variable in your model. I can also use the library which is a BLOR library, BLORR, and it will give me the output in much more organized format. I'll use the command line model GLM, same thing, binomial, link, logit, and the BLOR. If I want to get the output in organized format, the command line is BLR_regress model. Which model? This model. Yeah, option model not found, because I'll run the model, and you can see now how organized output I will get of logistic regression. I can also get the model statistics from here. Fit statistics, where McFadden's r-square, adjusted count r-square and everything, log likelihood, I will get it here. I can also get the model validation from here. There is a goodness of fit, that is a chi-square, and all the things also I will get it from here. How to interpret this model? Let us go back on the PPT and try to understand. Now we have created 3 models. That's a base model, fit1, fit2, and fit3. Okay, horsepower is significant, weight is significant. The important thing which we have to see is the Akaike information criterion of fit3 is minimum, and therefore we will select this model. We will select this model, right? In fit1, MPG displacement, horsepower and weight was there, which we dropped. Displacement was dropped in fit2. Further we dropped MPG also. Now we are getting the same accuracy, everything same, which we have seen in the classification accuracy. Even by dropping the variable, our classification accuracy remains same, and therefore we have achieved the parsimonious model, which is really good. All these codes are available in my book, Data Analysis Using R, which is available on amazon.in as well as amazon.com. You can follow me on LinkedIn and Twitter. Kindly subscribe to my channel.